Okay, I want to talk about atomic and molar mass. So, atomic mass is the mass in atomic mass units of one particle. Okay, now that particle can be atoms, it can be molecules, it can be formula units, it can be ions. So some examples here are carbon, it's 12.01 AMU per atom. CO2 is 44.01 AMU per molecule, and calcium carbonate's 110.10 AMU per formula unit. Okay, so those particles, most commonly we focus on atoms, molecules, and formula units. You could also talk about, say, ions, if you wanted to. Now, where did these values come from? Well, these values came from the periodic table. So you look at the periodic table, and you can find the average atomic mass. Okay, usually most periodic tables you'll look at are going to have two numbers along with the element symbol, and one of them, the whole number that increases as you go across the periods on the periodic table, that's actually the atomic number, which tells you the number of protons. But the other number, which most often has some decimal places to it, that is the average atomic mass. Okay, so that's the average mass of an individual atom of that element. Okay, so that's where I got the 12.01 AMU per atom of carbon. Okay, so I look at carbon on the periodic table, and the mass, the average atomic mass given there is 12.01. Now, of course, depending on what periodic table you're looking at, they may give you more decimal places. They're not going to give you less than that. You should always at least keep 2 decimals on all of your atomic masses. You don't want to round it to whole numbers because it can throw a lot of error into your calculations. And so you want to always keep at least 2 decimals so you're not, causing problems with your calculations. Now, the CO2, that comes also from the periodic table. It's just not directly there. You have to figure it out from what's given on the periodic table. Okay, so CO2 is not on the periodic table, but carbon is and oxygen is. Okay, and each CO2 contains 1 carbon and 2 oxygens. So you look up carbon and it's 12.01, and you look up oxygen and it's 16.00. Again, you can use more decimal places if you want, but around it, I will round it to 2. And so you would take that value and multiply the oxygen value by 2, and then you add it to the carbon. Okay, and that should come up with 44.01 AMU per molecule. And then calcium carbonate, we do the same thing. You look up the value for calcium, so 40.08, and you look up the value for carbon, again 12.01, and you look up the value for oxygen, again 16.00. Okay, and you would multiply the oxygen value by 3 and then sum them all together, and that should give you the 110.10 AMU per formula unit. Okay, so you should be able to add up the atomic mass for any element using a periodic table. You don't have to memorize the average atomic mass for anything. You just look it up on the periodic table. Okay, so all of these things are called atomic masses. It's masses on the atomic scale. Okay, on the order of individual atoms or individual molecules or formula units. Okay, now if you want to get really technical, atomic mass is the proper term for the mass of individual atoms. Okay, whereas this one for CO2, as I have indicated, is per molecule. That technically should be called a molecular mass. Okay, and so because it's the mass of a molecule, okay, but you can call it an atomic mass. That's what I'll do for simplicity. Similarly, for that ionic compound, since it is the mass of a formula unit, it more technically is called a formula mass. Okay, but we're going to just call it an atomic mass to keep things simple because it is on the atomic scale. okay? It's on the scale of individual units, okay, instead of clusters of these things. Okay, now molar mass, on the other hand, is the mass in grams of 1 mole of a particular particle. Okay, so atomic mass is the mass in atomic mass units, or AMUs, of one particle, whereas molar mass is the mass in grams of an entire mole of these particles. Okay, and so it is Avogadro's number of these things. Okay, but the nice thing about molar mass is it's the same value as atomic mass. Okay, it has the same value. The unit is the only thing that's different. Okay, so we've scaled up the moles. Okay, but the mass unit we're using is also scaled up. Okay, so carbon, when you look up on the periodic table and find 12.01, you can label that as AMU per atom if you're talking about it on the atomic scale, or you can label it as grams per mole. So that is the molar mass as well. Okay, and then you could do the same thing for CO2 and CaCO3. You can look up the individual elements, add up their masses, and you can label it either as AMU per molecule, AMU per formula unit, or grams per mole for those things. Okay, most often we work on the scale of moles. Okay, so we have sample sizes that are moles of things. Okay, we don't typically work with samples that are just a few atoms or just a few molecules. So we won't typically use atomic mass. Okay, so let's see. With that, I know it can seem kind of confusing. A lot of people don't like this. The number's the same, but I can magically just change the unit, right? But that's really how the AMU scale is set up. The AMU scale is set up so that it comes out to the same number, okay, as the number of grams in a mole of something, okay? So that scaling system is set up so that that is true. And so we can look at an example to show that these things are actually equal. Now I'll do it for a different substance. So I won't use carbon or CO2 or CaCO3. I'm going to use hydrogen. So if you look at the periodic table and then find hydrogen, and you get the molar mass or the atomic mass of hydrogen off of there, you get the atomic mass, it's going to be 1.008 AMU, okay, per atom of hydrogen. And we can convert that to a molar mass, you know, by actually showing conversions, things that we know are true. And what you'll find is the molar mass is going to come out to 1.008 grams per mole, the exact same numeric value, just as what I'm telling you. But let's look at that conversion so you can see where this comes from. So, like I said, I start with the atomic mass of hydrogen, right? 1.008 AMU per 1 atom of hydrogen. So that you get from the periodic table. And there's a conversion to convert AMUs to kilograms, okay? And so that's something you can look up, but I have it here that 1 AMU is 1.6605 times 10 to the negative 27th kilograms. So that would get rid of my AMU and tell me the number of kilograms per atom, okay, which is going to be very small. And we want it on the scale of grams because we want to talk about a molar mass. So I can convert kilograms to grams. 1 kilogram is 1,000 grams, okay? And so the kilograms part is going to cancel. And then I want it on the scale of moles, so on a per mole basis instead of a per atom. And so I can use Avogadro's number to get that. So if I put Avogadro's number on top, so the atoms on top, that will cancel with the atoms on the bottom that we started with and give me something in grams per mole. So if you punch that all in your calculator, what you will get is, again, 1.008. Okay, and it'll be 1.008 grams per mole. Okay, so those things are equivalent in numeric value, okay? It's just talking about things on a different scale, and so the mass unit is actually changing, okay? Okay, so that information, whether you're talking about an atomic mass or a molar mass, it's usually most useful to actually write it as a fraction. So in this listing of the atomic masses of carbon, carbon dioxide, and calcium carbonate, I listed them and had AMU slash atom and grams slash mole. But when you're actually wanting to utilize that information to do calculations, it's most often helpful to just rewrite it as an actual fraction, so it's more easily used in dimensional analysis. So like what you see how I have hydrogen written down at the bottom, so I can rewrite those things here. Let me erase this other stuff that's in the way. So you can look at the periodic table and get 1.008 for hydrogen, and you can write it in lots of ways, okay? So I have the atomic mass of hydrogen written as ratios, and I have it written both directions. So one hydrogen atom is 1.008 AMU of hydrogen, and I have 1.008 AMU over one atom as well. Or you can write it on a gram per mole basis, and again, you can write it either direction. So those are all just conversion factors that you can utilize to convert between your moles of something and grams, or atoms of something in AMU, if you wanted to go that route. We're going to focus on relating grams and moles, okay, using molar masses. So let's look at just the basic setup of how you would convert between grams and moles, or moles and grams of something, okay? And so if you want to go from moles to mass or mass to moles, you're going to always use molar mass, meaning you need to look at the periodic table and look up the values for each of the things that you're talking about. Okay, so we're just going to look at it a little bit generically first. If we have substance A and I want to convert, say, from moles of A to the mass of A, then I would set it up like this. Okay, so if I have moles, that's what I would start with, right? I would start with the number of moles, and then I would do dimensional analysis. And you can write that over 1 if you want, if that helps you see the dimensional analysis a little better. But we would have some number of moles given, and so we would take that value, and then we'd multiply by a ratio. And in that ratio, we would put moles opposite. So we start with moles, so we'd put moles on bottom, okay? And then we'd put grams on top. And then that grams on the top, that's the molar mass. That's the value you look up on the periodic table, the number of grams in a mole of whatever you have, okay? So you'd multiply that through, and that would give you the number of grams. So that would give you your answer, okay? Now, of course, you could convert this to some other mass unit if you wanted to, or if you were asked to. But using the molar mass is going to bring you directly from moles to grams or grams to moles, okay? If you want to do more conversions, you can add more steps, okay? Now, if instead we wanted to go in the reverse direction, then we would have a setup like this. We would have the mass that was given that we would start with. Again, you can put that over 1 if you want. So that's your starting amount. And if you want to convert from grams to moles, you're going to put grams opposite, so it's going to be on the bottom, and moles then in the remaining spot. So the grams are going to cancel in that case, and it's going to give you a result in moles, okay? So for that, you would take your grams, and then you would end up dividing by that molar mass, and that would tell you the number of moles, okay? So in this part, that thing that you're multiplying by, that is the molar mass of whatever substance you are dealing with, okay? But if you set it up using dimensional analysis and set up those units first, it's going to force you to put that number in the right location, because the number you look up on the periodic table goes with grams, okay? And then it's per 1 mole. So let's look at a couple examples to make sure you kind of understand what this basic setup is going to be for any conversion using molar mass. So the first one I have here is calculate the mass of 1.20 moles of potassium sulfate. Okay, so I have 1.20 moles of K2SO4. So that's what I'm going to start with. And I'm going to set this up as a dimensional analysis problem. Okay, so I'm going to be multiplying by a fraction. So as always, if you want, you can put that over 1. And I have moles. I want to get rid of that. So I'm going to put it opposite. So I'm going to put moles K2SO4 down here at the bottom. And I want the mass, okay, and molar mass is going to get me 2 grams. So I'm going to put grams on top, okay. So my units are set up to where the unit I don't want is going to cancel and the unit I want is going to remain, okay. And so now I need to figure out what numbers to put in here. Well, a gram to mole relationship, so a ratio between grams and moles, is the molar mass. So you're going to look at the periodic table and add up the masses of these things that are part of this molecule. So we have potassium. If you look at the periodic table, potassium is 39.10 grams per mole. Okay, and I need to take that times 2 because there's 2 of them in that formula unit of potassium sulfate. Okay, and then I have sulfur, and that's 32.07, and then that's grams per mole, and there's only one of those. Okay, and then I have 4 oxygens, and each individual oxygen is 16.00 grams per mole. And so I need to add that stuff. So 2 times 39.0 plus 32.07 plus, let's see, 4 times 16.00. And so that should come out to 174.27 grams per mole. Okay, so now that information goes into that ratio in my dimensional analysis calculation. So the grams is 174.27, and that's how many grams are in 1 mole of that. So now I can do my dimensional analysis. My moles are going to cancel. It's going to give me grams. So I'm going to take 1.2 and I'm going to multiply, or 1.20, and multiply by 174.27. So my starting value is 3 sig figs. My molar mass is 5 sig figs. So I'm going to round my answer to 3. Okay, so my answer is 209 grams of potassium sulfate. Okay, now let's do another one. This one says calculate the number of moles in 38.5 grams of nickel 3 sulfide. Okay, so I'm going to start with my 38.5 grams of nickel 3 sulfide. Okay, and I want to get rid of grams. Oops, and go to moles. That's what's being asked for. And so I need this ratio. I need to figure out what are the numbers that go into this ratio that relates grams and moles, and that would be the molar mass. So you're going to look up what nickel is, and nickel's 58.69 grams per mole, and there's 2 of those. And I'm going to add that to my 3 sulfurs, and each one's 32.07 grams per mole. And so let's see. Oops. Oh, so 2 times 58.69 plus 3 times 32.07. That gives me 13.59 grams per mole. And so that information goes into my ratio. So there's 213.59 grams in 1 mole of nickel 3 sulfide. So now my grams are going to cancel and it's going to give me moles. So I'm going to take 38.5 and I'm going to divide by 213.59. And I have a 3 significant figure mass and 5 sig fig molar mass. So I'm going to round to 3 sig figs again. So here it would give me 0.180 moles of Ni2S3. So that's the basic idea. That's how you can utilize molar masses to convert between grams and moles, okay? No matter which direction you want to go, okay? It's just one direction you're actually multiplying by the value, one you're actually dividing. But if you use dimensional analysis, you don't need to memorize how to do the conversions. You just follow the units.